La Niña, the cool sister of El Niño, is finally losing her grip. This climatic phenomenon, known for its cooler-than-average sea surface temperatures in the central and eastern tropical Pacific Ocean, has been a dominant force in shaping global weather patterns for the past few years. But now, the tides are turning. This climate pattern, characterized by cooler-than-average waters in the tropical Pacific, has held sway for the past few years. La Niña has been responsible for a variety of weather anomalies, including increased rainfall in some regions and droughts in others. Its influence has been felt far and wide, affecting agriculture, water resources, and even the frequency and intensity of tropical storms. But her reign is coming to an end. The ocean currents that once carried her cool waters are weakening, and the atmospheric conditions that supported her are shifting. Scientists have been closely monitoring these changes using advanced satellite technology and ocean buoys to track the gradual warming of the Pacific waters. As La Niña weakens, North America's weather remains in a state of flux. The transition period between La Niña and neutral conditions, or even a potential El Niño, can bring about unpredictable weather patterns. This means that regions accustomed to certain weather trends may experience sudden and unexpected changes. La Niña's influence on our planet is far-reaching. It impacts everything from ocean currents to atmospheric circulation. The cooling effect of La Niña can lead to a decrease in global temperatures, while also influencing the jet stream and storm tracks. It impacts everything from ocean currents to atmospheric circulation. The interaction between the ocean and the atmosphere is complex, and La Niña plays a crucial role in this dynamic system. By altering the temperature and pressure gradients, La Niña can change wind patterns, which in turn affect weather systems around the globe. As we transition away from this pattern, we can expect shifts in temperature and precipitation patterns across the continent. Some areas may experience warmer and drier conditions, while others could see increased rainfall and cooler temperatures. These changes can have significant impacts on agriculture, water supply, and even energy demand. Buckle up, North America, we're in for a wild ride. The transition period is often marked by extreme weather events including severe storms, heat waves, and cold snaps. It's a time when the atmosphere is in a state of flux and anything can happen. The transition between La Niña and its warmer counterpart El Niño is rarely smooth. El Niño, characterized by warmer-than-average sea surface temperatures in the Pacific, brings its own set of challenges. The shift from one pattern to the other can lead to a period of great atmospheric instability. It's a time of great atmospheric instability. The atmosphere is adjusting to the new conditions, and this can result in a wide range of weather phenomena. From intense storms to unusual temperature swings, the transition period is anything but predictable. This means we could see a mixed bag of weather in the coming months. As the atmosphere settles into a new pattern, we can expect a variety of weather events, some of which may be extreme. It's a reminder of the powerful influence of these oceanic and atmospheric patterns on our daily lives. La Niña has a distinct signature when it comes to North American temperatures. During a La Niña winter, the northern United States and Canada often experience colder-than-average temperatures. This year is no exception. Meanwhile, the southern U.S. tends to see warmer-than-average conditions. This north-south temperature divide is a classic hallmark of La Niña's influence. It's all about how this climate pattern redistributes heat across the globe. Think of La Niña as a giant air conditioner, pulling cold air down from the Arctic and pushing warm air towards the tropics. This creates a temperature seesaw across North America. As La Niña weakens, this temperature contrast will begin to ease. The jet stream, a fast-flowing river of air high in the atmosphere, plays a crucial role in steering weather patterns. This powerful current of air, which can reach speeds of over 200 miles per hour, acts like a conveyor belt, transporting weather systems across the globe. It is a key player in determining our daily weather and long-term climate trends. La Niña, a climate phenomenon characterized by cooler-than-average sea surface temperatures in the central and eastern Pacific Ocean, has a way of whipping the jet stream into a frenzy. This results in the jet stream dipping south over the eastern U.S. and surging north over the western U.S. These shifts in the jet stream can lead to significant changes in weather patterns, affecting everything from temperature to precipitation. This wavy jet stream pattern is responsible for many of the weather extremes we associate with La Niña. From intense storms and heavy rainfall to periods of calm and dry weather, the influence of La Niña can be seen in the dramatic swings in weather conditions. These extremes can have profound impacts on agriculture, water resources, and even our daily lives. In the eastern US, the southward dip of the jet stream brings cold air from the Arctic, fueling snowstorms and frigid temperatures. This can lead to severe winter weather, with heavy snowfall and icy conditions that can disrupt travel and daily activities. The cold air masses can also lead to prolonged periods of below freezing temperatures, posing challenges for heating and energy consumption. At the same time, the northward surge of the jet stream in the western US ushers in warm, dry air, increasing the risk of drought. This can lead to water shortages, affecting agriculture and increasing the risk of wildfires. The warm, dry conditions can also exacerbate heat waves, leading to health risks and increased energy demand for cooling. As La Niña weakens, the jet stream will gradually return to a more zonal pattern, meaning it will flow in a more west to east direction. This transition can bring a sense of stability to the weather, with more predictable and moderate conditions. The return to a zonal pattern can also help to balance out the extremes, reducing the risk of severe weather events. This shift will lead to more moderate temperatures and precipitation patterns across the continent. With the jet stream flowing more smoothly from west to east, we can expect a more balanced distribution of weather systems. This can result in more consistent rainfall, reducing the risk of both drought and flooding. The more stable weather patterns can also provide a respite from the extremes, allowing for a more comfortable and predictable climate. Section 4. High above a sudden heat, unmasking the stratospheric warming phenomenon. High above Earth's surface in the stratosphere, a dramatic warming event is taking place. This layer, situated between 10 and 50 kilometers above us, is experiencing a sudden and significant rise in temperature. This phenomenon, known as sudden stratospheric warming, or SSW, can have profound impacts on our weather, even though it occurs so high up. SSW events are characterized by a rapid increase in temperature, sometimes by as much as 50 degrees Celsius within just a few days. SSW events are like throwing a wrench into the gears of the atmosphere. They disrupt the usual flow of air currents and can lead to a cascade of changes throughout the entire atmospheric system. They disrupt the polar vortex, a swirling mass of cold air that typically resides over the Arctic. The polar vortex is a crucial component of our planet's climate system, acting as a barrier that keeps the coldest air confined to the polar regions. When the polar vortex weakens, it can wobble and even split, sending lobes of frigid Arctic air southward. This displacement of cold air can lead to severe winter weather in regions that are not typically accustomed to such extreme conditions. These SSW events can have long-lasting impacts on weather patterns, sometimes lasting for weeks or even months. The altered weather can manifest as prolonged cold spells, increased snowfall, and even shifts in storm tracks affecting regions far from the Arctic. Scientists and meteorologists closely monitor these events using advanced satellite technology and climate models. Understanding SSW is crucial for improving weather forecasts and preparing for the potential impacts on agriculture, infrastructure, and daily life. Historical records show that SSW events have been responsible for some of the most notable weather changes in recent history. For instance, the severe winter of 2013 to 2014 in North America was linked to a significant SSW event. The effects of SSW are not confined to the Arctic or even the Northern Hemisphere. These events can influence global climate patterns, demonstrating the interconnected nature of our planet's weather systems. Future research aims to deepen our understanding of SSW and its broader implications. By studying these high-altitude phenomena, scientists hope to unlock new insights into the complexities of Earth's climate system and improve our ability to predict and mitigate extreme weather events. Through visual representations and animated graphics, we can better grasp the intricate processes involved in sudden stratospheric warming. These educational tools help demystify the science behind SSW and highlight its significance in our daily lives. As we continue to unmask the stratospheric warming phenomenon, we gain a deeper appreciation for the delicate balance of our atmosphere and the powerful forces at play high above us. Understanding SSW is not just about predicting the weather, it's about safeguarding our future. Section 5. Greenland's high-pressure shield, a bulwark against the Arctic cold. One of the consequences of a weakened polar vortex is the development of high-pressure systems over Greenland and other polar regions. These high-pressure systems act like atmospheric roadblocks, diverting cold air southward into the mid-latitudes. Think of it like this. Imagine a dam holding back a river. The dam represents the polar vortex, and the river represents the cold Arctic air. When the dam weakens, the river is free to flow southward. These high-pressure systems over the Arctic are a key driver of winter weather patterns in North America and Europe. Section 6. Storms gather in the south. Low pressure's grip on Canada and the US. As high pressure builds over the Arctic, low pressure systems often develop over Canada and the northern United States. These low pressure systems are the breeding grounds for storms, bringing with them a mixed bag of precipitation, including rain, snow, and ice. The clash between cold air from the north and warmer, moisture-laden air from the south creates the perfect recipe for winter storms. These storms can bring significant snowfall accumulations, especially to areas downwind of the Great Lakes.